Okay, you're ready to go here. Hello, friends, and welcome to Science Talk. I am your host, Jim Massa, and in a continuing series of videos I've made discussing the weather that occurred in Alaska during 2019, and now, of course, continuing into the early part of 2020. I'm going to bring to you, I guess this is the fifth or sixth video in the series, but I'm going to bring to you the latest information. And for those of you who have not seen the prior videos, please check them out. Just click on the video tabs on my channel and scroll through and pull up those videos and look at them. And look at any of my videos there. All the videos I've made are there. So let's see what happened here. And several areas I'm going to be looking at, which is air temperature, sea surface temperature, and ice. Those are the sea ice. Those are the major things I'll concentrate on. I'll also be including sprinkled throughout this presentation some worldwide trends. So here we go. Let's okay, first of all, let's go through some acronyms because we'll be seeing a lot of them. So you have ACCAP, which is for climate and assessment policy. You have ERSST. SST is sea surface temperature, extended reconstructed sea surface temperature. ESRL is Earth System Research Lab, affiliated with NOAA. GODAS, Global Ocean Data Assimilation System. Then, of course, there's NOAA, which is the National Oceanographic Atmospheric Administration. That's the website, noaa.gov. NSIDC is the National Snow Ice Data Center, nsidc.org. They're located in Boulder, Colorado. And then you have the OISST, which is the Optimum Interpolation Sea Surface Temperature. And finally, PIOMAS, Pan-Arctic Ice Ocean Modeling Assimilation System. There is the URL. They have some excellent information there if you wish to go and check it out. Okay. So up to Utqiagvik, which is Point Barrow, Alaska. So this graph is showing the average annual temperature from 1921 to 2019. It's basically 98 years. And when you look at up until about 1988 or so, things were what they should be. Kind of a scatter shot. Things were pretty much average. Not much happening. The degrees Fahrenheit, so this would be about 9.5 degrees Fahrenheit. That's the average yearly temperature. The blue dots represent 10 coldest. The red dots, 10 warmest. But now look what happens starting in 1988. And the green line is the smooth average. You see what? You see a marked increase. Things are warming up. So it's gone from about 9.5 degrees and up until about 2019 or so, 2018, 2019, it's now at, looks like 17 degrees. 16.5, 17 degrees. That's a gain of approximately 7 degrees Fahrenheit. If you look at it in Celsius, that's going from about -13 to about -7, right? So that's about a gain of 6 degrees Celsius. So the Alaska 2019 Climate Review starts at the top. Utqiagvik had by far the warmest year in the past 99 years. I'm going to make myself disappear. You guys don't need to look at me. More the 11 degrees 6C above the pre-1980 average. 8 of the 10 warmest years in the 2010s. That's this right here. And here's 2019. 2019 is the warmest. 8 of the 10. Here's the 2010s. 1, 2, 3, 4, 5, 6, 7, 8. And then the ninth one is in 2008. And then we have to go back to about 1998 or so for the other one. Last 20 years, we've had 10 warmest years. And then 8 of the 10 warmest years occurred within this decade. If that's not a trend, I don't know what is. But there it is. So things a little slow here. What's going on? All right, there we go. Right. Yep. Okay. So now let's look at what it says here for autumn. Autumns have been trending warmer in Alaska in recent years, with both this year and last year in the top 10 in the past 95 years. This is in the NOAA ANCEI climate analysis. There hasn't been a top 10 coldest autumn since the mid 1990s. This is the last one. And it looks like, there's a slight cooling trend and then warms up significantly. Now, I have not seen the analysis of the regression line for this period from about, 1922 or so to about 1992 or so, to see if that, if the slope is significant or not. Basically, if the slope is significantly different from zero, that means something is happening. If the slope is not significantly different from zero, that means basically we have a flat line. There's no relationship. So I would need to see what the R square value for that is and what the analyses indicated. 10 cold, yes, look at the warm years, right? We got them here. This is statewide. This is the entire state of Alaska. So we've had some warm years before. We've had some cold years. Makes sense, right? The last 2 years have been very warm. So now here's the statewide average December temperature for basically, we're talking a 113-year record. And again, it's pretty flat line, slight increase here. Again, it would be interesting to see if the slope test is significantly different from zero or not, to tell us if there's a trend or not. And this is from the Berkeley Earth data set. Average December temperatures for Alaska since 1895. No surprise that 2017 is the mildest, and 5 of the top 10 mildest are since 2000. Right here. 1, 2, 3, 4, 5. Those red dots there. 1914 is right up there. No December since 1980 is even close to making the 10 coldest. Not even close. Look at the scatter shots here. Not even close. Now, this is an interesting graphic. So basically what I've shown you in the prior graphics is that things are warming up, right? These are air temperatures we're looking at. Things are warming up in Alaska. So now this is the number of days where the minimum temperature is less than or equal to minus 34. This is in January, December, as recorded at the Fairbanks International Airport. Now, a little caveat. For some reason, the airport tends to record temperatures that are a little bit warmer than the rest of the surrounding region. Bear that in mind. So this is year by year, again, January through December, okay? And so what do we see? The number of days. So in this year, we had 52 days, 51, 52 days, where it was 34 below. This is in Fahrenheit or colder. Look at this one here it looks like it is 53. This is about 1955. You had 56 days of 34 below or colder. Now, as you can see, it kind of oscillates here a bit. Now, I think you guys would know why if you've watched all my videos. this is being driven in part, not totally, but in part by the Arctic Oscillation. For example, the January that just, and this does not include 2020, but the January that just concluded here in Fairbanks was the coldest, in fact, for the state, was the coldest January in 25 years. Part of that was because of the extremely, very strong negative indicators for the Arctic Oscillation that gives us a very strong zonal tight flow. So the cold temperatures was kept up at high latitude. Now, when you look at the parameters that go into determining the index, if you look at the historical data for those parameters, we should have had temperatures in the minus 50, 55 to 60, 65 realm. Instead, our temperatures was 30 to 40, 42 below. Yes, it was cold, but it's not as cold as it has historically been. So yes, this exemplifies how us scientists, us climatologists, we tease out the data. We tease out the natural signals from the human signals. And the natural signals, yes, we get this sort of stuff here. The human signals that were not for global warming, were not for us burning fossil fuels, it would have been a hell of a lot colder up here. So, and as you can see in this graph here, the trend is very clear. It's just dropping down. I mean, the last time we saw any number of days, 34 below or colder above 40 is basically in the mid-60s. 1978 is really interesting. No days, didn't get that cold. And look down here also as well. And then of course that's 2018. There's been winters here up until this winter. It's like I was hardly getting anything near 30 or 40 below. And even with the cold temps that I had at my house, the coldest I saw was 36 below, 38 below, which is really not that bad. So this it's an interesting graph showing a trend of the number of really cold days is decreasing. And you can see it's basically for a 90-year period. Okay, let's look at the Alaska statewide temperature. This is from Berkeley Earth gridded data from 1850 to 2019. And this is year by year. Every available data set agrees 2019 was the warmest year on record for Alaska. The last 6 years are indicative of a climate regime shift. That's this clustering right here. It just goes from bang, and now this looks like, see these little oscillations here? Well, now we're oscillating at a higher value. And this is on the vertical scale is the departure from the 20th century average. So 0 means there's no departure. So if you look at, for example, 1875, there was no departure. The average temperature agreed with the average. And saying, you look at here, that's 1977 is very close, maybe 0.1, minus 0.1 C, pretty close, as is 1995 and so on. But you can see it kind of oscillates around some spikes, but then we get to shoot up here, and now it's it's starting to show a new trend up here. It will be interesting to see how this plays out over the next 3-4 decades. But I would not be surprised if it does indicate a climate regime shift towards warmer conditions. Okay, this is a loaded graphic here, and I encourage you to pause the video playback, and if you want to really examine and scrutinize these slides here. 15-year trend in high temperatures at the top and low temperatures at the bottom for all 4 seasons, spring, summer, fall, and winter, from left to right. So spring, summer, fall, winter, and then this is the upper 4 are the high temperatures, and the bottom 4 are the low temperatures. So what do we have here? Changes in spring high temperatures in the last 15 years. Basically, where you see yellow, orange, and red, it's gotten warmer. Gray is pretty much unchanged. Okay. If you start seeing light blue to dark blue, that means cooler. Now, in a quick examination of all of these slides here for Alaska, indicates pretty much what? Things are either, if they stayed the same, or they got really much warmer. And where they get really much warmer is in springtime and in wintertime. Look at that. Look at that. So basically, the summers are warmer. Okay, the springs are warmer, the summers are warmer, the winters are warmer, and even the low temperatures are higher. Now, having said that, this January did set a record for the lowest high temperature ever recorded in Alaska, in Fairbanks, and that was 4 degrees Fahrenheit. That was the lowest high temperature. In other words, the entire month of January, it didn't get any warmer than 4 degrees Fahrenheit. I'm now sitting at, it was cooled down because the sun set down, but today it got up to like 10 above, 12 above. So it's that system that brought this the cold temperature for those weeks is breaking down, and but we're getting snow, whatever. But yeah, this shows you how the state is really warming up. Now, if you look here, if you look at like the Midwest is showing a cooler trend, as Texas here, that's in the fall. Pacific North, the high plains, the Pacific Northwest showing a little cooler winter. So, and why is that? Well, that's the jet streams dipping down. The meridional flow is changing, so the jet stream is dipping down, bringing the cooler temperatures, and when it dips down, it goes right over the middle of the continent. So, if you wish to, just pause the video and look at this some more. So now, Alaska statewide daily temperature index. So this is from, here's January 2011, then January 2012. So each of these hash marks is the January. So this is the year in between. So this is 365 days. So this is daily temperature index. Okay. Alaska statewide temperature index. So the list of the years from 2011 to 2019. Percent days above normal, percent days below normal, average index score. So starting in 2011 is 51 and a half days. And, this is the lowest, 2012, 37.4, 60. That's almost 71 in 2014. Look at 2016. It's almost 88 days of the year. That's like 3 months worth above normal temperatures. And see the same thing in 2019. And when you look at this here, the percent days below normal is becoming fewer and fewer. So the average index score, look at that, 5.5 degrees. So the Alaska statewide temperature index finished up 2019 with 318 days above normal. Nice, that's percent. 318 over 365, 47 below normal. While extreme, it's not a one-off year. Every year since 2014 has seen 2/3, every one of them, or more of the days average warmer than normal. That's a statewide scale. And if you want to go back to 2013, 60% or more. Yeah. The Arctic is warming up, folks. And what happens in the Arctic does not stay in the Arctic. It does affect the planet. So as you can see here, okay, here's where we have some cooler days and so on. This is in January 2012. Right? You can see we had more percent days below normal than above. There was a La Nina event, and also the early part of 2013, almost even, but still is more days warmer than average and then cooler above average. But then when we start getting into the later years here, with an occasional, couple week stretch or whatever, or a little dip down, it's all up here in the red. I mean, there's a lot more red than there is blue. 2019 was the warmest year on record since 1925 for 8 of the 13 climate divisions in Alaska. This is again based on a NOAA and CEI climate analysis. Only the eastern Gulf Coast was the second warmest, and the Panhandle have had a milder year. That's this stretch here, right? This is the eastern Gulf Coast that's being referred to, and the Panhandle, right, down this way. Panhandle heading down to Ketchikan and so on. The entire state is warmed up. If you look carefully, you can see some of these lines here that indicates the climate divisions, right? 1, 2, you can count them out here. The Aleutians are warm, and to Diomedes and so on. So midwinter, December through February, Alaska regional temperature trends over the past 50 years, again from the NOAA ANCEI climate. Winters on average now are much milder than 50 years ago. And yes, the math is correct. That's Brian Brett Schneider who tweeted this, and he gets a little tired of people questioning his mathematics. He knows what he's doing. But as you can see here, this is telling us how much warmer it is from average. Statistically significant trend. So this is basically over the last not quite 40 years. So if there's white, trend is not significant. Yellow, it's +1 to +2 degrees F, and so on. But really, with the exception of the Panhandle, where we got a little bit of this, light orange, and you have some darker orange, most of the state is red, or this, I guess, raspberry color. But there you have it. Fairbanks is in this locale, so this region here, the Middle Tanana Valley and so on, saw 8.2 degrees Fahrenheit warmer from average. Wow. Now, part of this is also the fact that the sea ice forms later in the year, so the ocean's absorbing heat. There's latent heat energy that is given off. That helps keep things milder. It'll also bring us some more precipitation events. And I'll be talking more about the sea ice situation later on. This is really cool. The area average annual mean temperature for Alaska. Okay, so this is the annual temperature in degrees Celsius. Okay, and give you a couple of data sources here. The NCEI Climate Division, which is NOAA, then ERA5 reanalysis. Correlation is 0.99. That means the data is really well put together. So it starts from 1920 up to 2020, so about a 100-year cycle. According to Climate Division, Alaska's NOAA ANCEI climate, Alaska's annual mean temperature was above freezing for the first time in 2019. Right there. That sort of tickled in 2017. There we went above it. For the first time, for the entire state, that's from Ketchikan up to Barrow, out to the Aleutians, whatever. First time the entire state had an average temperature above freezing. Typically, the average temperature for Alaska is in the realm of about -3, -4 C. About 26, 27 degrees, something like that. So ERA5, 2-meter temperature from Copernicus ECMWF. 2-meter temperature means recording the air temperature at 2 meters above the ground. That's what that means. Now, the ER5 shows a slight bias typical for reanalysis data. And this is courtesy of World Climate Service, and that's the Twitter handle. But this Average temperature, not just a one off or a bounce up or a couple of days. The entire, taking into account the entire year, average temperature above freezing. That's a big holy shit. Now, this is mean surface temperature, not to be confused with sea surface temperature. This is mean surface temperature. So this is air temperature near the surface. And the important thing to look at here is, okay, the 5 warmest average January through November, right? January through November, global air temperatures have all occurred within the last 5 years. So the 5 warmest average temperatures from January to November occurred the last 5 years. I call that a strong trend. But here's the interesting thing. Look here in the North Atlantic, over Greenland, right, Labrador, and so on. This is the NAO. Got this persistent little cooler spot here. But look at the Arctic. Look at the northern latitudes. Look how much warmer things are. And this is crazy. 2016 is the warmest. Look, this is this purple here, or lavender here. That's this color here. That's that guy. Holy crap is what I say to that. But as you can see, it's pretty much the entire planet is warmer than usual. And this is in January through December. Now, of course, for down here, this is their summer. Right? When the Northern Hemisphere is having a winter, January, November, January is summertime in the Southern Hemisphere. November would be, January is our winter. January is their summer. November is our winter, and that's their summer. So yeah, that's their summer down there. So June is summer for us. It's winter for them down in the Southern Hemisphere. But it's warmer. And this is courtesy of Zach Labe, and that is Twitter handle. Here's the 2-meter temperature worldwide from January through December 2019. This is the ranks. This is for the entire globe. Overall rank for the entire globe is 2 out of 71. Percent rank number 1 is 8.8%. Percent rank number 71 is 0.0%. So what does this mean? Okay. Number 1, 8.8%. Ranks it from 1 high to 81 low. So a ranking of 1 is 8.8% of the entire globe. When you get to 2, it changes over. 71, the lowest, 0.0%. In other words, the deviation is trending so that things are getting, for the most part, warmer. Now, the middle of the North Atlantic continent, the Eastern Pacific off South America and heading down towards Antarctica does show less ranking. There's less warming. It's still warming, but not as strong as what we see here for Eurasia, for northern North America, for the Pacific Ocean, for most of the Atlantic Ocean, with the exception, kind of the spillage from the Labrador Current down this way, mixing in with some mesoscale eddies. Here's an interesting thing. Look at the average temperature from latitude 90 to minus 90. That's North Pole to South Pole, longitude 0 to 360. In other words, the meridian at Greenwich, England, all the way around. So translation, this is the entire globe. Okay, temperature C. It's going up. Here's 2019. It's going up. Earth had its second warmest year since record keeping began. Only 2016 was warmer, and not by much, like 0.3 degrees C. Now, the percent of the selected area covered by each rank. Okay, so here's this first thing, 8.8%. Now, if you look at the second rank, you can then count that looks like about 5.8 or so. Then you've got, for the next one, for 3, you've got, looks like about 6.4 or so. So you can see how it quickly drops off. Most of the planet is warming up. So if you wanted to, you can actually sum up this thing here, and you would be able to get a percentage of how much has warmed up by whatever temperature cutoff you want to examine. The take-home message from this here is that the planet is warming up. You look at this right here. You can easily fit a regression line through that will have a significant positive slope telling us that the planet is warming. That is the take-home message from this graphic I want you guys to take with you. Okay, now let's go and start looking at what's going on with the sea ice. The Port of Nome was handling operations on November 27th, the latest on record. Usually frozen up by then. November sea ice concentration near Nome has fallen off the proverbial cliff in the past decade. This is data from ACCAP's Historical Sea Ice Atlas. That's the URL if you're interested in checking that out. So the record goes from 1900 to 2019. It's about 120 years or so. And what this is showing is the average concentration of the sea ice, how much sea ice is there. So this is kind of a 11-year running median. And then look what's happened starting in about 2008, 2009. It's tanked. In fact, you look at the last decade, very, very little sea ice hanging around in November near Barrow, near Nome. This is up Nome, which is where the Iditarod ends. Surrounding Nome in November, and that's the trend for the last decade. Now, running a median, right? The median is the 50th percentile. Okay. I did a quick little example on my population video where I discussed the difference between average or mean and the median. So the median is the 50th percentile. In other words, half the data is above that value, half the data is below that value. And they do an 11-year running median. So meaning that they take the medians for like years 1 through 11. Okay, calculate that. Then you go from years 2 through 12, calculate that median, 3 through 13, etc. And you just keep going with that. And that's what this green line illustrates. And that's why it starts here at 1910, because 1900 and 1910, right? You include 1900 through 1909 is 10 years, and then 1910 is the 11th year. So that's why the graph starts, at least the green line starts there, because you had to take the median of those years prior. Then we go to 1912, and you go from 1912 to 1901, and so on. But again, the take-home message is, in the last decade, there's been no sea ice of anything to write home about around Nome in November, and as a result, it's dropped off dramatically. And we see the red dots. That means there's no sea ice. So looking at the Bering Sea, okay. So here's the Bering Sea. There's the Bering Strait. Here's the Chukchi Sea, the Beaufort Sea. Point Barrow, Utqiagvik is up there. Nome is about there. You go across Norton Sound. Okay, it's about in that area. And so what do we see here? The ice extent in square kilometers. So this gives you the ice extent, the vertical bars, and then this is the smooth average. Once again, the trend is very clear. There's been a general decline, starting for sure about the late 1990s, and continues to decrease up until the present. Bering Sea ice extent is the lowest of record for December 18th in the 42-year NSIDC data, less than a third of the 81 to 2010 average, though not too different of the past from 3 of the past 4 years. Bering Sea daily ice extent, basically over the last 40 years. Again, so looking at pretty much the same region. So the black line is the 81 to 2010 median. So if you look at this black line, you can see about half of it, half of these light gray lines are above it, half of them are below it. So sea ice extent again in square kilometers. Now, we're still in the 2019-2020 winter season, so that's why it stops there, the blue line. Okay. But look at the green line, 2018 to 2019. It's well below what is typical. Same thing for 27, 2018, well below typical. Ice extent is far below the long-term average, third lowest of record for the date. Weather pattern looks good for continued ice growth at least another week. That's because of those cold temperatures that was in January. And this was updated December 28, 2019. It was cool at that point there, but the temperatures really hadn't started to decrease significantly. There were some cool spots around that time, around Christmas. But January definitely cooled down. Now let's go to the Chukchi. This is the autumn ice over date. Again, approximately 40-year data set. The Chukchi sea ice extends up to about 96% of the basin. This is in the NSIDC data. This makes December 22nd the third latest for first date in the autumn for extent to reach 95% or more. That's a day after solstice, winter solstice. The trend is extreme. Ice over is now typically 4 weeks later than about 1990. And here's 1990, and here is the line shooting up. Ice over data. In other words, the trend for when we get to 95% of the basin is covered with ice. It's getting later and later. That's what this is telling us. Right? The first autumn date extent where you have 95% of the Chukchi is covered with sea ice. And this, starting in 1990 or thereabouts, the trend is increasing, telling us it is getting later and later on average. That's what this is telling us. Now, I just have to put in this photograph because this is Little Diomede, Alaska, December 17, 2019. Gay Sheffield, I know her. She's a really nice lady. From Tuesday afternoon in the Bering, she actually does a lot of her research on walruses. So she's, yeah. From Tuesday afternoon in the Bering Strait, looking southwest from Little Diomede. This is open water. In December, open water. It's usually frozen over. That's Big Diomede, Russia, right here. This is Russia. So if you plop Sarah Palin down here, then when she says, I can see Russia, then she would be telling the truth. There was some sea ice on the north side of the island, that's to be expected, but water to the beach at Wales, which is pretty much what this, I think this was showing. This is open water here. This is right in the middle of the Bering. This is crazy. So this is like water in between the islands here. That's Russia. That's Alaska. It's just absolutely insane. And when you have open water like that, any latent heat energy is going to be given off, and that helps modify temperatures. Okay, now we're going to look at sea surface temperature. Okay, January to December. Spoiler alert, warmest decade. So University of Alaska Fairbanks, the data source NOAA, ranks it based on 119 years of data. So decades since 1900 with the highest average sea surface temperature. For 72% of the globe, the current decade through 2018 has the warmest sea surface temperature. Focus on the red areas, not the blue areas. Red areas, right? Blue area is that North Atlantic Oscillation kind of being a little bit of a trend buster. Now, what's this blue spot off of Antarctica? There's actually a current that's right there. It's very cold, salty water, and that's going to affect the sea surface temperatures here before that cold, salty water takes a dive. Okay. This is part of the Jin Sea. So again, we're having the Gulf Stream giving off its heat, the Scandinavia and the UK and that kind of stuff, before it sinks, forming the North Atlantic deep water return current. So these spots here, you have the NAO, it also is affecting things, but the deep water formation there and there is why those areas are blue, a little cooler temperature. So basically what this is telling us is the entire ocean is pretty much warming up. So when you look at this green patch here, green patch here in the North Pacific, that looks like it's this color here. So 1960 and 1970 was its warmest decade. Okay. But most of the oceans, 2010 to 2018 is the warmest decade. Then you have this orange is 2000 to 2010. And then you can, this yellow and then that yellow is 1980 to 1990 and so on. Think of how much energy the oceans are absorbing. Remember, specific heat of water is much, much higher than air. So it takes much, much more energy to heat up the same given amount of water, 1 degree C, as does the same given amount of air, 1 degree C. So this is a shitload of energy that the oceans have been absorbing and continue to absorb. But remember, gas solubility decreases with increased water temperature. At some point, the oceans will stop absorbing the CO2 from the atmosphere, and it may then turn around as it continues to warm and start to outgas the CO2 back into the atmosphere, jacking up the levels even in the atmosphere even more so. Keep that in mind. It's an important concept I cannot stress enough. And now, this is, 1900 and 2019. Let's see, sea surface temperatures have warmed at a statistically significant rate since 1900. Any area in orange or red, stay focused on the red areas. Okay, there's that deep water formation, the deep water formation. What do we see here? We see that the oceans have significantly warmed, at least sea surface temperatures. Okay. So, percent significant greater than 0.95 is 97.6%. In other words, this is a statistical value that they're giving here, percent significant. Purple is negative. About the only negative I see there, and a little tongue there, and one there. Otherwise, it is pretty much red. So these are basically standard deviations away from the mean. And it's very, very significant. Let's look at the warmest and coldest decades, years ending in 9. Since 1900, using NASA GISTEMP data, red is the 2010s. 77% of the Earth just had their warmest decade. 0% had their coolest decade. So what had their coolest decade? Well, this little patch in the Southern Ocean in the 40s. And then in the 30s and 40s, and again, that North Atlantic, and that's because that's where the Jin Sea cools down and so on and so forth. This is the planet is warming up. This shows it right here. The planet is warming up. Let me repeat this. 77% of the Earth just had their warmest decade. 0% had their coolest decade. That leaves 23%, and 23% is going to be in the orange and the darker yellow. That pretty much takes care just about the remaining 23%. You might have, there might be something like 18% remaining. The planet is warming, folks. This is the data that demonstrates that fact. Now let's look at the warmest and coldest decades. Okay. So the previous showed the warmest decade. This now shows the coldest decade. In the 1910s, maybe into the 1920s or 1900s. So in other words, this dovetails with this statement: 0% had their coolest decade in the 2010s. Most of the coolest decades were in the early part of the 20th century. That's what these two graphs show. Warmest in the 2010s, 0% had the coolest decade in the 2010s. The coolest decades occurred in the early part of the 20th century. That's what this is showing. Now, this is an interesting one. Oceanic heat content anomalies in the upper 300 meters. Again, looking at standard deviations. So we're going from 5 standard deviations below the mean to 5 standard deviations above the mean. Overall rank for the entire globe is 1 out of 39. Again, that's looking at these guys here at this histogram. So basically, technically a bar graph. But here we've got, the first ranking is pushing 5 and it continues on down. So what this is showing is oceanic heat content anomalies. The green through the yellows, orange, and red shows that it is warmer than usual. Is that gray blue? Whatever. The gray blue into the purple is cooler than usual. Where do we see that is cooler than usual? Southern Ocean, North Atlantic, middle of the Atlantic, right here in the middle of the Pacific. That might have something to do with the gyre that's right there. This is basically averaging over 300 meters. This is considerably warmer. This is considerably warmer and warmer. This graph here, right? Average potential temperature for 66 degrees north latitude to 74 degrees south latitude. Okay, 66 degrees north latitude is basically from here, kind of the Bering Strait. 74 degrees south latitude is pretty much the start of the Antarctic continent. And what we're seeing here is, again, the strong, unmistakable trend that the oceans is warming up. This is down to 300 meters. Now, it would be, if they showed 100 meters, there'll be a lot more in the yellow, orange, and red. But they're taking it down to 300 meters, which actually is downplaying how much warming has occurred in the surface. But it's taken into account some mixing. But if they were to look at the upper 100 meters, you would probably see most of the ocean surface, at least 80% in the orange, yellow, red region. But the trend is unmistakable. Starting from, again, about the late 1900s, definitely by 2000, it's going up. So this map shows anomalies and standard deviations from the 81 to 2010 average, and the 30-year average. The upper 300 meters was the highest on record in 2019. Trend line is ominous. That's this red dot here. Think again how much energy the oceans have absorbed in order for this to be seen and measured. Now, percent of the Earth with the warmest and coldest decade since 1900. And that's what you really ought to be looking at right there. The last 20 years has just shot up. Percent of the Earth experienced the warmest decade since 1900. Brian has a very dry sense of humor. It's as if something has changed. Yeah. Burning fossil fuel. Blue is coldest, red is warmest. Now, if you want a hockey stick graph, there you have it. Okay, so that kind of brings us to the end of this little presentation. Again, I wanted to, as I've done before, I want to acknowledge the source where these graphics are, courtesy of. So many graphics and figures are courtesy of Rick Tolman and Brian Brettschneider, both associated with NWS, the National Weather Service, part of the International Arctic Research Center. The NWS is located within IARC on campus. They're both meteorologists. Brian Brettschneider is based in Anchorage. I don't know if I've mentioned that in prior videos. Rick Tolman is in Fairbanks. And so they're their Twitter handles. And other graphics are courtesy of Zach Labe at the ZLABE, World Climate Service, ACCAP, GODAS, NASA, NOAA, NSIDC, PIOMAS, other agencies and contributors indicated on the slides. And make sure to always leave a point to leave on the slides where the data is from. Though these figures have yet to be published in peer-reviewed journals, they do take time. You're probably impressed. They reflect the latest data and can be assumed to be accurate, and I can vouch for that. Because I remember when I was working there, seeing the oceanographic data coming in hot off the press, which is, i.e., a download from the satellite. so there you have it. Kind of showing you what's going on with Alaska, and then I expanded it to worldwide. So what is the take-home message? The take-home message is that the planet is warming. It's warming significantly in the last 10 to 20 years. The oceans are absorbing a shitload of heat energy. The air temperature is warmed up significantly. The upper ocean layers are warmer than the departure is higher than the average. It's warming up significantly, which will start changing weather patterns. And we're seeing this, right? We're seeing the fires in Australia and California, Scandinavia, Alaska. We're seeing the temperature swings, the precipitation outbursts, etc., etc. So this can be traced to human activity. There is no doubt about that anymore. Anyone who wants to still deny this doesn't know what they're talking about. So there you have it. I thank you for your time, and we'll talk soon. So where's the second? Hey folks, it's a reminder to please share my videos with others, and to also please tell others of my channel. Please subscribe, and don't forget to hit the bell so that you receive notifications when I upload new videos. I also hope that you will consider supporting the work that I do and supporting this channel by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.